Welcome to This Explainer. You know, mathematics really isn't just about crunching a bunch of random numbers. It's a beautifully designed architecture. Today, we're going to explore the foundational language of this architecture, starting from how we logically group items together all the way to how we handle unimaginably large quantities.
But before we get into the heavy lifting, let's kick things off with a quick puzzle to get our gears turning. Think about this. Do you happen to know what the first and actually the only even prime number is? Hold on to your guess, because the answer reveals something super fascinating about how numbers are categorized, and we'll get to that very shortly.
Here is our roadmap for today. We're going to cover the world of sets, visualizing with Venn diagrams, exploring types of numbers, and finally, mastering standard form. Let's jump right in.
Part 1. The world of sets. Mathematical grouping. Let's dive right in and see how mathematicians actually sort the universe of data. At its core, a set is really just a collection of objects, which we describe by a specific list or a rule. For instance, you could have a set of odd numbers, or a set of very specific values like 1, 3, and 5. But mathematics is so incredibly thorough that we even account for, well, nothing. The empty set, represented by those curly brackets with absolutely nothing inside, or that 0 with a slash through it, is quite literally the set with no members. It's kind of the mathematical equivalent of putting an empty box on a shelf and officially labeling it as empty.
Now, when we start comparing these sets, it is absolutely vital to know the difference between a union and an intersection. The union of set A and set B, written with that U-shaped symbol, brings everything to the party. It includes all elements that are in A, or in B, or in both. But an intersection, written with the upside-down U, is much stricter. It isolates only the shared elements, just the items that manage to exist in both A and B at the exact same time.
Moving on to Section 2, Visualizing with Venn diagrams, seeing the overlap. Sometimes just reading the mathematical rules isn't quite enough, right? We need to actually see the overlap. And this brilliantly illustrates our exact definitions of intersections, unions, subsets, and complements using the classic overlapping circles of a Venn diagram. Notice how the intersection is visually represented by just that shaded middle ground where the circles cross. The union, meanwhile, highlights both entire circles. We can even see a subset where one entire circle sits completely inside another. That just means every single member of set B is also a member of set A. But the crucial point here is actually that rectangular box wrapping around the circles. That is the universal set, usually denoted by that curly E. It contains absolutely every element being considered in a particular problem. If your circles are categorizing certain data points, that outer rectangle is the ultimate boundary. Literally nothing outside of that box exists in that specific mathematical universe. All right, Section 3, Exploring Types of Numbers, the core ingredients. Now, this is a concept we really need to focus on because understanding unique types of numbers completely unlocks higher math. And hey, bringing it right back to our opening puzzle, the answer is 2. The number 2 stands completely alone as the first and absolutely the only even prime number in mathematics. Because every other even number is obviously divisible by 2, they immediately fail the prime number test. It's a perfect example of how a number's specific type, being simultaneously even and prime, gives it completely unique properties that no other number in existence shares. Let's expand on this, because numbers behave very differently based on their specific classification. Take an integer, for example. An integer is simply a whole number. It's clean, it's precise. But then, look at the irrational number. This is a number type that stubbornly, and I mean stubbornly, refuses to be written as an exact fraction. By simply defining a number as an integer versus an irrational number, you completely change what mathematical operations are even possible and how that number interacts with the world. Now, what's really wild about this is how the simple rule of integers forms the absolute foundation of one of history's most legendary math puzzles, Fermat's last theorem. The theorem states that there are no integers, x, y, and z, which have a solution to x to the power of n plus y to the power of n equals z to the power of n when n is strictly bigger than 2. Notice that absolutely crucial word, integers. If you allow different types of numbers, like irrationals or decimals, this equation would be a total breeze to solve. But by restricting the type of number exclusively to whole integers, Fermat created a problem that took mathematicians literally centuries to figure out. It perfectly showcases the immense power of number types. Which brings us to our final section, Section 4, Mastering Standard Form, Managing the Massive. So what happens when our numbers become just too enormous, or maybe too microscopic, to write out traditionally? Well, standard form is the mathematical solution for dealing with vast scale. It allows us to process massive data points without getting lost in a sea of zeros. Instead of meticulously counting digit after digit just to figure out if you're looking at millions or billions, standard form condenses everything into highly manageable powers of 10.
Looking at this direct translation, you can instantly see the utility. You can see how 4.56 times 10 to the power of 2 effortlessly unpacks into the ordinary number 456. Or check out the next one. 6.7 times 10 to the 7th power is exactly the same as 67 million. It is an incredibly efficient shorthand for scaling numbers way up or way down. And standard form isn't just for writing things down neatly. It makes actually doing the math much simpler. When you're faced with daunting calculations, like 6.8 times 10 to the 6th multiplied by 3.1 times 10 to the negative 4th, standard form turns the impossible into the easily solvable. You're able to handle the core numbers and the powers of 10 separately, completely streamlining what would otherwise be some incredibly messy arithmetic. As we wrap up this explainer, I want to leave you with this final thought to chew on. How do the logical rules of sets, the unique quirks of different types of numbers, and these massive standard form calculations shape the everyday dimensions of the real world around you? These foundational tools of mathematics aren't just abstract rules trapped on a textbook page. They are the very blueprints used to measure, understand, and construct our universe. Keep looking for these patterns out there, and I'll catch you in the next explainer.